Alright, hello. I'm so sorry that I'm late. I had a multitude of tech issues and I also came back later than I was expecting and I had to eat some food. But yeah, I hope everyone's doing okay and I hope that this stream goes okay. Unfortunately, the software that I use to multi-stream, it's not like combining the chats correctly and stuff, so if I missed your message, I'm so sorry. I don't mean to. I'm gonna try to read chat more often if anyone is chatting. But yeah, hello. I'm excited. I've been wanting to do a stream like this for a long time. I used to do these more often, but it's been a while. And I wanted to try like going through a whole textbook eventually. But I think today it will just be like the first chapter or two. I did see the textbook a little bit, so it'll be a surprise. I think chapter 1, I'm only going to go through half, because actually, I have a video on the first part of chapter 1. But yeah, I'm excited. And, oh here, so I have the textbook and my notes. Back to my horrible penmanship. Yeah, so this book is free. It's like an open source book, you could say. But yeah, if you would like to follow along, or in your own time, if you want to read it or go ahead or do anything, I do plan on having this much more often, like having this as a series almost. But I will definitely have to see. So here's the textbook. It's free. The website is linked there. It's like open source and stuff. So we'll go and look at the table of contents. So I am gonna skip these sections and I'm gonna start at 1.5. So I actually, like I said a while back, I made a video on unit conversion dimensional analysis and I included a little bit about standards. So yeah, if not, I mean, I don't think this should be hard. I will go back to it if anyone wants me to, but I think estimates and Fermi calculations are where I'm going to start. And then hopefully we can get to vectors. And then the next time I do this, let's learn about position, displacement, and velocity. But yeah, that's the plan for today. Hopefully I get to it. And, oh, wait. Hold on. I have so many tabs open because my streaming software is not working, but I am going to also have background music before I forget, just a little bit. Just a little bit of background music. Oh my gosh, this is so scuffed, I'm so sorry. I think, yep, it should be playing. Hopefully it's not too loud or not too quiet. You can turn it up. Maybe it's too quiet right now, just a little bit. Yeah. Yeah. Sometimes my background music stops because it's like, are you there? So I will need to be checking that as well. But hello. So let's write down the section that we're doing. So we put like chapter 1. You're gonna see my horrible penmanship. Actually, it's been like a super long time since I've done any physics like this, so I'm gonna be relearning it as well, and hopefully you'll be able to pick up on something, or maybe you're interested in something. So put chapter 1-1.5, and put estimates. And Fermi calculations. Okay. I'm still not used to using my little tablet pen thing. So page 24. Let's find page 24, page 10, 12, 16, 19, 20. Also, if my giant head is like blocking anything important, please do tell me. Sometimes I forget, or maybe I should move my ginormous head somewhere else. 24, we're here. Yeah, actually I am gonna move myself. Let me move myself like here. There we go. I think that's better. That's better. That seems better. And every time I tab out, I have to re-get my tabs. Oh well. Okay. So, estimates and Fermi calculations. It's too loud. I think my background music's too loud. This is so messy. This is so scuffed. I'm sorry. The next time I do this, I should be more prepared. And I think, yeah, okay. Estimates and Fermi calculation, learning objectives. By the end of this section, you will be able to estimate the values of physical quantities. Ah yes, a very important skill. So I did remember something that my professor once said. He was saying that you should always check if a value is like reasonable or not. So for example, if you want to bake a cake, like a single small cake for yourself, if you see a cake, do you think of like, if I say go buy like 10 pounds of flour for one cake, that's not reasonable. But if I say buy, you know, a few grams, I don't know how many grams a cake needs, but like 300 grams of flour or something, that seems more reasonable. And I remember him telling like us a story in class that there's once this famous physicist, I don't know who, but his entire job was just to tell people whether or not something was reasonable or not. Good afternoon, hello, hello! Anyways, so I'll stop yapping and start reading. I'm not that good at reading because I stutter a lot and I can't read too well, but I'll try my best. Okay, on many occasions, physicists and other scientists and engineers need to make estimates for a particular quantity. Other terms sometimes used are guesstimates, order of magnitude approximations. I remember that. Part of the envelope calculations or Fermi calculations. The scientist Enrico Fermi mentioned earlier was famous for his ability to estimate various kinds of data with surprising precision. Maybe it's this person. Will that piece of equipment fit in the back of the car? Do we need to rent a truck? How long will this download take? About how large a current will be there in this circuit when it's turned on? How many houses could a proposed power plant actually power if this is built? Note that estimating does not mean guessing a number or a formula at random. Rather, estimation means using prior experience and physical reasoning to arrive to a rough idea of a quantity's value. Because the process of determining a reliable approximation usually involves the identification of correct physical properties and a good guess about the relevant variables, estimating is very useful in developing physical intuition. So you need to develop physical intuition, I guess. Estimates allows us to perform sanity checks on calculations or policy proposals by helping us rule out certain scenarios or unrealistic numbers. They allow us to challenge others as well as ourselves in our efforts to learn truths about the world. Many estimations are based on formulas in which the input quantities are known to a limited precision. As you develop physics problem-solving skills, which are applicable to a wide variety of fields, you will also develop skills at estimating. Okay, you develop these skills thinking more qualitatively by being willing to take risks. As any skill, experience helps. Familiarity with dimensions and units and scales of base qualities also help. So we have skipped this part, but if I think we need to go back, we can go back. Make some progress in estimating. You need to have some definite ideas about how variables may be related. The following strategies may help you in practice practicing the art of estimation. Get big lengths from smaller lengths. When estimating lengths, remember that anything can be a ruler. Thus, imagining breaking a big thing into smaller pieces or smaller things, estimate the length of one of the smaller things. So basically, use small things to estimate big things. Is what I'm hearing. And multiply to get the length. Yes. For example, to estimate the height of a building, first count how many floors it has, then estimate how big a single floor is by imagining how many people would have to stand on each other's shoulders to reach the ceiling. Last, estimate the height of a person. The product of these three estimates is your estimate of a height of a building. It helps to have memorized a few length scales relevant to the sorts of problems you'll find yourself solving. For example, knowing some of the length scales in that table might come in handy. Sometimes it also helps to do this in reverse, that is to estimate the length of a small thing. Imagine a bunch of them making up a bigger thing. For example, to estimate the thickness of a sheet of paper, estimate the thickness of a stack of paper, then divide by the number of pages in the stack. These strategies of breaking big things into smaller things or aggregating smaller things into bigger things, or big thing into a bigger thing, can sometimes be used to estimate other physical quantities such as masses and time. Wow, okay. So, maybe we'll write that down. I know this could be intuitive for like a lot of people, but for the sake of being consistent with notes, let's write down. So lengths. Use small and big things to estimate each other. So I'm put small, and then I'm gonna put like an arrow pointing both directions. Things. There's THINGS, right? Things, and then estimate. 2. Put this one in capital letters. Estimate, except the last 2 letters apparently. Estimate. Yeah, and then let's move on to the next section. So, get areas and volumes from length. When dealing with an area or a volume of a complex object, introduce a small model of the object such as a sphere or a box. Then estimate the linear dimensions, such as the radius of the sphere or the length, width, and height of the box. First, use your estimates to obtain the volume or area from geometric formulas. If you happen to have an estimate of an object's area or volume, you can also do the reverse. That is, use standard geometric formulas to estimate of its linear dimensions. So if you want something that's like 2D or 3D, so for area, you're gonna try to estimate the linear dimensions and use the formula. So we're gonna write area, and the ampersand. I can never draw the ampersand correctly. It's like, that's not it. Hold on. It kind of like goes like that, and, right? And volumes. Areas and volumes. So, what you're gonna do is find or estimate the linear dimensions and use formulas. But use geometric formulas. Geometric formulas. Nice. And continue. Get masses from density and volumes. Oh, I see what this book is doing. So it's going from like individual lengths to the areas, and then it's going to keep going down. So after you find the volumes, you can find density from and mass from the volume. I see. Get masses from volumes and densities. When estimating the mass of objects, it can help first to estimate its volume, and then to estimate its mass from rough estimate of its average density. Recall density has dimension mass over cubed or length cubed, so mass is density times volume. Yes. For this, it helps to remember that the density of air is around 1 kilogram per meter cubed, and the density of water is 10 to the 3 kilogram per meter cubed. So from this, I can already tell that for volume, you want something with like kilogram per meter cubed. So it is just a unit of mass over a length cubed. And the densest everyday solid is max around 10 to the 4th kilogram per meter cubed. Ask yourself whether an object floats or sinks in either air or water gets you a ballpark estimate of its density. You can also do this the other way around. If you have an estimate of the object's mass, its density, and you can use them to get an estimate of its volume. Okay, so you're going to want to use the mass is equal to density times volume equation a lot. So we're going to write the titles still. So masses from volume. I guess I should start changing colors. No. Can never get the ampersand correct. Volume and density. And from this, we break down that equation. So mass is equal, and I'm just going to use M for mass, is equal to volume density, or put D times volume, so dV. And then once you find the volume, and you know the mass, you can get either one. And how dense something is. So I guess you can compare the density to water and other everyday objects. Compare, or I should say, know scales of everyday objects and compare. Know scales of objects and compare. And then objects, and then put a comma, and then compare. Yeah. That seems good. Whoa, I didn't mean to do that. I need to... That's not the right one to pick. Oops. Okay. Compare, and then from that we can put like water is water is 10 to the 3rd kilograms per meter cubed, and then air is very light. I don't think we'll... Maybe I should put air? Yeah. So air is not very dense at all. So we'll have that as the scale. That does not look like a cubed. Oh, I can right click. Thank you. Thank you, computer, for telling me that you're telling me that I'm stupid and that I need to learn how to do this. Anyways. So, if all else fails, bound. bound it. For physical qualities for which you do not have a lot of intuition, sometimes the best thing you can do is something like, well, it must be bigger than this and smaller than that. For example, suppose you need to estimate the mass of a moose. Maybe you have a lot of experience with moose and know their average mass offhand. If so, great. But for most people, the best thing you can do is to think something like, it must be bigger than a person. So people around 10 squared kilograms, and less than a car, which is 10 to the third kilograms. If you need a single number for a subsequent calculation, you can take the geometric mean of the upper and lower bound. That is, you multiply them together and then take the square root. For the moose mass, this example would be that. Okay, so they're going to teach us how to bound it. We should write down the example. And then to bound it, you have two values, and you want to take the geometric mean. Two values. You want geometric mean. Put the example, so we have 10 to the 2 to 10 to the 3. OMG, what subject do you teach? I don't teach a subject. I'm too stupid to teach a subject. I'm just trying to relearn, and we'll see what happens. And I did not mean to click that. My pen. I'm still very not good at using my tablet, which sucks. Alright, so this is what we're bounding. We're going to take the geometric mean. I don't know why I put an S. Geometric mean. There should not be an S there. So we'll have this. So that's one value multiplied. I'm just going to put a dot for multiply instead of an X, because I like to use X to represent values, maybe later on. And then, quite frankly, I'm not going to do this by hand, and you can just stick it in a calculator. So it's going to be around here. So I guess the moose that we're trying to find is going to be around 3 times 10 to the 2 kilograms. The tighter the bounds, the better. Also, no rules are unbreakable when it comes to estimation. If you think the value of the quantity is likely to be closer to the upper bound than the lower bound, then you may want to bump up your estimate from the geometric mean by an order of 2 magnitude. Okay, so if it's closer to the upper bound, then you can bump up the estimate by magnitude of 2, so I guess it's like times 2. I find all Indian teachers on livestream YouTube, I can't understand them. It feels sad. Oh, I think it's because they're too smart. That being said, I don't know. I find that like all the Indian YouTubers who do teach on YouTube, I've never seen a live stream, to be fair. They're always super helpful, but sometimes they go so fast, I'm like, okay, I need someone to slow down. Yeah, I'm just doing this for fun. I'm not really a teacher. I'm trying to relearn this myself, and once upon a time I used to actually know this, but I don't anymore, so here we are. 1 sig fig is fine. There's no need to go beyond one significant figure when doing calculations to obtain an estimate. Okay, in most cases, the order of magnitude is good enough. The goal is to... Oh wait, when they say magnitude, do they mean by like times 10? I guess it would depend. Depend on what you're estimating. In most cases, the order of magnitude is good enough. The goal is just to get the ballpark figures, so keep the arithmetic as simple as possible. Ask yourself, does this make any sense? Last, check to see whether your answer is reasonable. Yes, the most important part of this is whether or not your answer is reasonable. How does it compare to the values of other quantities with the same dimensions that you already know or can look up easily? If you get some wacky answer, for example, if you estimate the mass of the Atlantic Ocean to be bigger than the mass of the Earth, or sometimes span longer to be longer than the age of the universe, first check to see whether your units are correct. Then check arithmetic errors, then rethink the logic you used to arrive to your answer. If everything checks out, you just proved that some slick new idea is actually bogus. Alright, so the most important part, if we want to have a takeaway, maybe I'll put it in like a different color for important takeaways. I don't like red. Red is such a bright color. Maybe I'll try blue or like a darker blue. Yeah, that looks okay. Let me erase that though. Okay, important takeaways. Reasonable. Reasonable. And if it's not, then check errors and check errors. Check errors if it's not reasonable. Hopefully my enormous head is not blocking this. Check errors. There we go. So when we look at units, then arithmetic. That's supposed to be an arrow. You know, this would have been nice when I was learning it, to like have a process, because oftentimes I'd be like, why is it wrong? And I just wouldn't, because I forgot to check the units first. I forgot to check the units first, but my number was actually correct. And then rethink your logic. Logic. There we go. Here is an example. Are we almost done with this section? We are almost done with this section. Let me switch back to black pen. Okay, mass of the Earth's oceans. Strategy. We know the density of water is around 10 to the third kilograms per meter cubed. So we start with the device to get masses from densities and volumes. Thus, we need to estimate the volume of the ocean's planet. Using the device to get areas and volumes from lengths, we can estimate the volume of the oceans as surface area times average depth, or V times AD. So to get volume, surface area, which is A, and then depth is D. So it's like a box. You're basically making this an enormous box. And then finding like the volume of that. We know the diameter of the Earth is... Okay, I don't actually know the diameter of Earth because I skipped this part. But we can go back to it. And we know that the Earth's surface is mostly covered in water. So we can estimate the surface area of the oceans being roughly equal to the surface of the planet. By following the advice to get areas and volumes from lengths again, we can approximate Earth as a sphere and use the formula of the surface area of the sphere of a surface area of the sphere of diameter d. So this is the surface area of the Earth. You just use an entire ball and then you use that to estimate the surface of the ocean. We just need to estimate the average depth of the oceans. For this, we use the advice. If all else fails, bound it. So we can use the geometric mean to bound it. We happen to know the deepest points in the ocean to be around 10 kilometers, and that's 10 kilometers, and that it's not uncommon for the ocean to be deeper than 1 kilometer. So we take the average depth to be around this. So let's write down what's happening. Maybe I will pick a different color. Even though English is not my primary language, you speak it very clearly. I hope I am. English is my primary language and the only language I know, really. So I hope it is clear. Maybe I'll have examples in green, like the end section examples. So we'll put example, estimate mass of Earth. And I will go back to that chart. Oh, I cannot spell. Okay, even though English is my only language, I struggle with spelling and reading, to be honest. I stutter a lot, and that's not the best, but I can't really do anything about that. Earth, ocean. Alright, so we can estimate volume of oceans by getting the surface area and the depth. So volume equals to area and depth. Think of like a big box. Just like if you want a volume of a box, you get the area of one of the faces and then the depth of it. And then we also need the area or surface area of the sphere. So we need surface area of the sphere. Area of sphere. S-S-S-P-H-E-R-E. Here we go. I need the diameter of the Earth. So if I click on this, will it take me to this? Yes. Where's the Earth? The diameter of the Earth. 10 to the 7th. So Earth diameter, we'd have that equal to, that looks like a V. My handwriting is so bad. I'm so sorry. Meters. I noticed that this is in meters and not kilometers. So we might need to change that, and I think we were on page like 26 or something. Roll back down. And we're too far. There we are. I found the section. Okay, and we need to know the depth of the ocean. So I'm gonna draw like an arrow down here, and we will bound it because we don't actually know how deep. The ocean always, like, the surface floor changes a lot. So we're gonna bound it to get an estimate of like an in-between number. So bound. My ginormous head blocking. Let's move it up there. That seems good. Bound it. So the ocean is somewhere between 1 kilometer to 10. And this is in meters, and I guess the book changes it into meters. I was actually going to change this into kilometers, but we change it into meters. So 1 kilometer is equal to 10 to the 3rd meters, and this is by unit conversion and dimensional analysis, times 10 to the 4th meters, and then you square root that. I actually don't prefer writing that in a decimal. I like doing it like this, but I don't think it matters too much. 3 meters. So now we need to just put it all together. Heating the device, the 1 one significant figure is fine. So like one value. So this 3 is one significant figure. Alright, so let's find the surface area of the Earth. That's what they did next. So we're going to use this equation, the surface area of the sphere. Take that, multiply by pi. I actually don't have my calculator with me, and I should calculate it on my own as well. But I'm just gonna trust the answer that the book gives. Squared. Yeah. Okay. And then find the volume of the oceans. Which would be A times D. So you take this value, put it into A. So I'm gonna put like a... Does it make sense? Like if I put an arrow here? So I don't... That way it's all in steps, and you can see why I calculated it like this. I think that would be nice. Or is that too hard to understand? It's just better I just write it. And then we know that the density is given from this. So, well then, if I do that arrow, then I would have to do this as well. There we go. And then we can have the volume equal to 9 times 10 to the 17th meters squared. Or cubed, not squared, cubed. And then mass is... I should write that equation down as well. So mass is density times volume. That I need to put. So we're gonna have density times volume equals mass. And we want to find the mass of the ocean. So we need the density, which we have this times the volume. Right? Yeah. How do we get this value, though? Hold on. Oh, density of water. I should have wrote that one down. Okay, hold on. Density of water. And this is not even density, this is depth. I don't know why I thought that. My bad. I'm sorry. Density of water. Because of the oceans. Yeah, we want to find the mass. So we take that. We have volume right here. So that's 9 times 10 to the 17th. Maybe I will just rewrite it. I think that would be easier. I wanted to see if like adding arrows would be more smooth, but I think it's just making it look complicated. And then we have the density. Kilograms per meter cubed. Right, you multiply that. And you can check the units as well. So we have, let's do unit check on the side. Unit check. We have mass cubed. Wow. Mass cubed times kilograms. And we should get kilograms because we want to get the mass. Which we do get. So yay! Multiply this. You end up getting 9 times 10 to the 20 kilograms. Apparently. Apparently so. I should actually calculate. Hold on, let me get a calculator. I will not be doing this by hand. Hello, Blue. Hello, hello. Sorry I'm late and can only lurk. No problem. Thank you for saying hello. I appreciate it. And thank you for lurking. I need to find my calculator and I can't find it. Alright, so, yeah, I still can't find my calculator. We'll just trust the book, yeah? You can do this on your own time. I'll do what professors always tell you to do. You can calculate this on your own. I'm sure it works out like this. So, thus we estimate the order of magnitude of the mass of the planet's oceans to be 10 to the 21st in kilograms. And then talk about how you can verify the answer. Does this make any sense? It's reassuring that our estimate 10 to the 21st kilogram for the mass of the Earth oceans falls somewhere between these two. So yes, it does seem to make sense. It just so happens that we searched on the web for, mass of the oceans. Top search was this, 1.4 times 10 to the 21st kilogram, which is the same order of magnitude as our estimate. Now, rather than having to trust blindly whoever first put the number on the website, most of the other sites probably just copied from them after all. We have a little more confidence in it. Yes, yes. And here's some other stuff. Shall we move on to section 1.6, significant figures? Did my music stop? It stopped. My music stopped. Keep playing, please. There we go. Let me zoom out a little, just to make sure it's sort of in a straight line. And now you can like zoom back in. Should be around here, I think. So next section is significant figures. We'll have chapter 1, 1.6, and significant figures. Or like I like to call them, sig figs. Significant figures. Okay, we are on page 27, and for anyone who would like to follow along, this book is completely free. It's like open source, so yes. Good day, Barry, and everyone chat. Hello! Thank you for waving. I'm gonna take a sip of water because my throat is gonna give out from reading so much. See how much more, alright. Maybe I'll do like 2 or 3 more sections, and then we'll see how far we get. I originally wanted to get to chapter 2, but reading, I didn't realize how much reading affected my voice. Alright, by the end of this section, you'll be able to determine the correct number of significant figures for the results of a computation. Describe the relationship between the concepts of accuracy, precision, uncertainty, and discrepancy. Calculate the percentage, or the percent uncertainty of a measurement. Oh, that's important. Give its value and its uncertainty. Determine the uncertainty of results of a computation involving quantities and given uncertainties. Jeez, I can't read. So, this image right here shows 2 instruments used to measure the mass of an object. The digital scale has mostly replaced the double pan balance in physics labs because it's more accurate and precise measurements. But what do we mean by accurate and precise? Aren't they the same thing? In this section, we examine in detail the process of making and reporting a measurement. Funny enough, when I was in this is gonna make me sound really old, but I actually some of my physics classes had this. It didn't look this rusty though. Maybe this one's just is even older. I've had both, but we did use this once. I'm an ancient person. And here's the figure. So basically they're both used to measure mass. And masses are typically metal cylinders of standard masses such as 1 gram, 10 grams, and 100 grams. Many mechanical balances such as double balance pans have been replaced by digital scales, which can typically measure the mass of an object more precisely. The mechanical balance can only read the mass of an object to the nearest tenth of a gram, but many digital scales can measure the mass of an object to the nearest 1,000th gram. So this is more accurate and precise, right? Yes. Accuracy and precision of a measurement. Science is based on observation and experiment. That is, on measurements. Accuracy is how close a measurement is to the accepted reference value for that measurement. For example, let's say we want to measure the length of standard printer paper. The packaging in which we purchase the paper states that it is 11 inches long. We then measure the length of a paper 3 times and obtain the following measurements. Oh, okay. So they took 3 pieces of paper and measured it, and then got these values for how long the paper is. These measurements are quite accurate because they are very close to the reference. In contrast, if we obtain a measurement of 12 inches, our measurement would not be very accurate. Notice that the concept of accuracy requires that an accepted reference value be given. So let's write that down. I'll write it down as accuracy and precision. ACC. Accuracy and precision. And we'll write down what accuracy means, which is being close to an accepted reference. We'll put close to. Let me make that a little bit more spaced out. To an accepted. Why do I write my letters so close to each other? And that's too far. Accepted reference. I'll put ref as REF and then an abbreviation. And then next we have precision, which I haven't actually done yet. Let's write a line for it. The precision of measurements refers to how close the agreement is between repeated independent measurements. So how close between repeated independent measurements, which are repeated under the same conditions. Okay, same conditions, yes. Consider the example of the paper measurements. The precision of the measurements refers to the spread of the measurement values. One way to analyze the precision of the measurements is to determine the range or difference between the lowest and the highest measured values. In this case, the lowest value was 10.9 inches and the highest value was 11.2 inches. Thus, the measured values deviate from each other by at most 0.3 inches. These measurements are relatively precise because they did not vary too much in value. However, if the measured values had been 10.9 inches, 11.1, and 11.9, then the measurements would not be very precise because there would be a significant variation from one measurement to another. Notice that the concept of precision depends only on the actual measurements acquired and does not depend on an accepted reference value. So, seems like precision means how close your measurements are every time you do a measurement. So we write precision. Precision, wow. Okay, that is... No, I can't. This is so ugly. I swear my penmanship on real paper is not this bad. Probably. I mean, it is. It isn't. I've been told I had decent handwriting. Precision. Anyways, how close independent measurements are. So we'll write close independent measurements. Put measurements. E-A-S-U-R-E. Yes, E-M-E-N-T-S. Close measurements. And this one is an accepted reference. So I am actually going to highlight that, or just underline, I should say. Not highlight. Either be... So this one relies on the accepted reference, and this one relies on independent measurements instead. Okay, let me close the pen. The measurements in the paper example are both accurate and precise. But in some cases, measurements are not accurate, some measurements are accurate but not precise, or they are precise but not accurate. Let's consider an example of GPS attempting to locate the position of a restaurant in a city. Think of the restaurant location as existing at the center of a bullseye target. So I guess this will be the analogy. So like the restaurant will be right here. And think of each GPS attempt to locate the restaurant as a black dot. In this figure, we see the GPS measurements are spread out far apart from each other, but are relatively close to the actual location of the restaurant at the center of the target. So this one is accurate because the reference is the center one, and you can see that the dots of where it says, the GPS says where the restaurant is quite close to the main circle in the target, or the main red circle in the target. This indicates a low precision, high accuracy measuring system. Low precision, high accuracy. So if you notice that each of the dots are spread out, so they're not close independent measurements. However, they are technically close to the accepted reference. However, in this figure, the GPS measurements are concentrated quite close to another, but they are far away from the target location. This indicates high precision and low accuracy measuring system. So we can see that the points of the GPS are saying that it's all the way here. They are very close together, so the independent measurements are close together, but they are not close to the main circle in the target. So that's where the restaurant is. Next up, we have uncertainty and discrepancy. The precision of a measuring system is related to the uncertainty in the measurements, whereas the accuracy is related to the discrepancy. Okay, so that seems important. We'll put a dot here. We'll put uncertainty. And I am gonna use an alpha symbol. if I can draw it. Usually the alpha symbol means when you use that symbol when something's proportional to something, but I'm not gonna use that in that way. So I'm not very, there we go. That's an alpha. So this just means related to, for now, at least. Maybe later in the book it will say like, oh, this is proportional, but I'm gonna use this symbol as related to. And then I'm gonna put precision. Precision. And we're gonna have discrepancy. And that is related to... Why? Why can't I do that? There we go. Discrepancy is related to accuracy. There we go. Uncertainty is a quantitative measure. Quantitative measure of how much your measured values deviate from one another. There are many different methods of calculating uncertainty, each of which is appropriate to different situations. Some examples include taking the range that is the biggest. Some examples include taking the range that is the biggest, least, less the smallest. Oh, I see. Or finding the standard deviation of the measurements. So they're trying to calculate uncertainty. So this is like finding the error in some sense. Discrepancy or measurement error, or I guess this is the error. Well, they're both kind of errors. But I guess standard deviation and finding the differences between the range is uncertainty, and discrepancy is measuring the difference between the measured value and the expected value. Okay. If the measurements are not very precise, then the uncertainty value is high. If the measurements are not accurate, then the discrepancy of the values is high. Recall our example of measuring paper length. We obtained the measurements of this. So the 11.1, 11.2, and 10.9 inches. And the accepted value was 11 inches. We might average the three measurements to say our best guess is 11.1 inches. In this case, our discrepancy is 11.01 and 11.1. Okay, so let's show like a discrepancy example, or maybe I'll show one later. I'll still write it in the notes, because why not? So we'll just have discrepancy. Discrepancy. So you average the three measurements. So average measurements. Average measurements, then take the expected value and subtract it by the average value. Expected minus average measurements. And that is our discrepancy. So I'll do, I don't know, I think it's kind of useless. I'm not the best at taking notes, so if you guys have anything, like any format that you don't understand or something, like what you don't understand what I'm writing, please put it in the chat. But yeah, expectancy is equal to this. It's not going to fit on the page, but we'll just leave it like that. Which provides the qualitative quantitative, I can't read, quantitative measurements of accuracy. So yes, we get the quantitative measurement of accuracy. We might calculate the uncertainty in our best guess by using half of the range of our measurement values. By using half of the range in our measurement values? What does that mean? By using half of the range of our measurement values. 0.15 inches? Then we would say the length of the paper is 11.1 inches plus or minus 0.15. Half of the range. I still don't really get how they get this 0.15. Half of the range in our measurements. 2, 3. Oh, okay, I see what they're doing. So they're taking like the differences between these values from the smallest one to the biggest one, which is 0.3, and then dividing that by 2, and that is sort of their plus or minus 0.15. I see what they're doing. So we'll have uncertainty. Okay, my giant head is not blocking it just yet. So we'll take smallest value minus largest value. Small, or I should say largest value, because then it won't be negative. Largest val minus smallest val value and then get something. I don't know what to. We'll call it x. Just that value as x. Divide by 2, and that is our uncertainty value. Or uncertainty. Yeah, that'll be our uncertainty. Genius head. No, I just have a big skull and nothing in it. Okay, that'll be our uncertainty. I see what they're doing. And then you can report it as like value plus minus uncertainty. Okay, my head is not blocking just yet. I will move the paper up though. That's a Y, by the way. Gosh, my penmanship. Oh, like over here. Move it up a little more. The uncertainty in a measurement, A, is often denoted as delta A. So we have the delta symbol. So the measurement results would be recorded as that. Okay. That's good to know. I'm gonna have it. I don't know, how do I make a delta symbol? Like that? A. We'll have it written like this, just right next to the title. Returning to our paper, the measurement length of the paper could be expressed as this. So value plus the delta of that value. Since the discrepancy of 0.1 is less than the uncertainty of 0.5, we might say the measured value agrees with the accepted reference value to within experimental uncertainty. The measured value agrees with the adopted reference, okay, value to within experimental uncertainty. So it agrees with the uncertainty of this. Because it has low discrepancy, so you would say that it's accurate. I see. Some factors that contribute to uncertainty in a measurement include the following: limitations of the measuring device, the skill of the person taking the measurement, irregularities in the object being measured, any other factors that affect the outcome, highly dependent on the situation. In our example, such factors contributing to the uncertainty could be the smallest division on the ruler is 0. Contributing factors to uncertainty could be the smallest division on the ruler, which is 1 to the 16th inch. The person using the ruler has bad eyesight, alright? So if I use a ruler, then it'll be harder to see. And therefore, I can't get the accurate decision. The ruler is worn out on one end, or one side of the paper is slightly longer than the other. At any rate, the uncertainty in a measurement must be calculated to quantify its precision. If a reference value is known, it makes sense to calculate the discrepancy as well to quantify its accuracy. So both are important. Percent uncertainty. Another method of expressing uncertainty is a percent of the measured value. If a measurement A is expressed with the uncertainty delta A, the percent uncertainty is defined as this. Okay, instead of using X, I'm actually going to use A, since this, I think, well, no, because that's still X. That would not be A. A is the actual value, not the subtracted value. Never mind, ignore what I said. I'm still going to be using X for this, or at least in this context. And percent uncertainty. Wow! What's wrong with my C? Okay, there you go. T-A-E-A-I-N-T-Y. So we have that, which is equal to the change, the uncertainty of A over the value of the A, and then times 100 to make it a percent. Alright, example time! And then, well, I guess I should make a closing statement, right? Did I make my example? No, I made the important parts in blue. So let's do that again. This is right, like, what's the takeaway of this section? So we need to know, like, accuracy versus precision. Where did my pen go? Okay. Important parts are in blue. So accuracy versus precision, you gotta know that. Accurate versus precise. And then we need to know discrepancy and uncertainty. So discrepancy, which is related to accuracy, I'm gonna put like the little delta symbol that I use to denote being related to it. Discrepancy and uncertainty. Yeah, there we go. And then reporting things, so reporting that how do I sum that up? Oh, I should say results are results reported like this. Results LT as results. There's a U. LT results are reported like this. So they have the value, the uncertainty of the value, and then you can also check the discrepancy. Make sure that it's not super high. Low or high. Discrepancy. There we go. Let's move on to the example then. Bag of apples. I used green for no. Okay, that dot is gonna annoy me. There we go. This is so scuffed. I'm so sorry. I need more water as well. I'm out of water. Let me get more. I'll be right back. Make sure to drink water for yourself as well. I noticed that if you have a hydrated brain, there's more brain power, you know? You gotta fuel your mind. Get some water. Right, I'm back. Now let's go to the example. I have example and then bag of apples. How do I name it? Okay, just put example in the bag of apples. I'm trying to make it consistent, or like the way I label things kind of consistent. So that everyone can understand my notes. I might like post these later. Maybe I won't. I don't know, it's too embarrassing. My handwriting looks terrible. Maybe I won't post these. If I ever do more physics stuff and my notes actually start looking better, I might post them. Bag of apples. I mean, this video is always gonna be here on YouTube. Okay, a bag of apples. Grocery store sells 5-pound bags of apples. Let's say we purchase 4 bags during the course of a month and weigh the bags each time. We obtain the following measurements. So these measurements for expected value of 5-pound apples. So we'll write expected 5 pounds. You know, one thing I am surprised about this book is how many English units there are in examples. Usually physics books don't have like pounds or inches. It's always like, kilograms or grams and centimeters or meters. It's fine, easy to understand my writing. Really? I don't know. I don't know. So we'll have the list of apples. It's supposed to be 5 pounds and you got one that's 4.8. Bro, that's a scam. You got scammed that day. I guess the next day, or the next week. You got scammed that week, but the next week they made up for it. We got this. Then determine the average weight of the 5-pound apple bags is this. So let's calculate this. So the average, we would add them all, and this is where I need my calculator. I can't find my calculator. I can't believe it. I'll just use my phone calculator, but I don't really like it that much. I want to calculate it first, just to make sure that I'm doing it correctly. Okay, so let's calculate the average. For that, you just take all the values. 3 plus 4.9 plus 5.4, and then you divide that by the number, so that'll be all divided by 4. Which you get 5.1, so that's the average. Hi, hello! And then now let's calculate the uncertainty, which you would take the highest value and the lowest value. So the highest value is 5.4 minus 4.8. And then take that and divide that by 2. Yes, I get 0.3. Okay, I am doing this correctly. What is the percent uncertainty? So we got exactly the same value they reported. So we can put 5.1 plus or minus 0.3 LB. And then we need to find the percent uncertainty. So we can take this equation. So first we observe this, and that uncertainty this. Then we can just plug it in, right? Yeah. Oh, my ginormous head is blocking. Again, my bad. Here's the equation. I subtracted the highest and the lowest value, divide that by 2, and then you get the 0.3. Sorry. I forget that my head just blocks the screen sometimes. So we can use the equation. Times, I'm gonna put 100 and then put percent equal to 0.3 over 5.1 times that 100, which they said was around 6%, or 5.9, which is basically 6%. There we go. We conclude that the average weight of the apple bags from this store is 5.1 plus 5.1 pounds plus or minus 6%. Notice the percent uncertainty is dimensionless because the units of the weight in... Oh, the units do cancel in this, like, the percent uncertainty equations cancel. Maybe I'll write it with the units just so that you can see that it cancels. So LB over 5.1 LB, and then 100 is just to make it into a percent, so that, or to get rid of the decimal places. Wow, my dyslexia. Hold on. I switched those two. I'm lucky I caught that one. Okay, there we go. So then this crosses out with that. And then it's dimensionless. Let me check the ratio. So you can report the final answer as 5.1 pounds, and then plus or minus a percent. So that percent in this case is 6%. And this is our final answer for the bag of apples, which is actually quite good, because it's supposed to be 5 pounds, but you get a little bit more apples. Unfortunately, the first week you got scammed. Oh, there's more. How much more is there to this chapter? Okay, let's finish chapter 1. I think I can do it. Or chapter 1. Chapter 1's almost done, hopefully. Uncertainties in calculations. Let's see. Uncertainty in calculations. Uncertainty exists in anything calculated from measured quantities. For example, the area of a floor calculated from measurements of its length and width has an uncertainty because the length and width have uncertainties. Wait, what? There's too many words in that one. For example, the area of a floor calculated from measurements from its length and width. Okay, you're just finding the area of the floor has an uncertainty because the measurements have uncertainty. I see. So because each individual measurement has an uncertainty, when you use it to calculate another quality of something, that also has uncertainty. Okay, that makes sense. How big is uncertainty? And something you calculate by multiplication or division. If the measurements going into the calculation have small uncertainties, a few percent or less, then the method of adding percents can be used for multiplication or division. Okay, this method states the percent uncertainty in a quantity calculated by multiplication or division is the sum of percent uncertainties in the items used to make the calculation. For example, if a floor has a length of 4 meters and width of 3 meters, with uncertainties of 2 and 1% respectively, then the floor of the area is this. So you multiply 4 times 3, which is 12 in meters squared, and has an uncertainty of 3%, so 2 plus 1, expressed as an area. This is 0.62 meters squared, which we round to 4 since the area of the floor is given 1/10 of a meter square. I see. Okay. That makes sense. So let's switch back to the black pen. And then we will make a note on uncertainties in calculations. Uncertainties in... Not bad. Why is my handwriting like this? I swear it's not actually this bad when I write on paper. So you want to use the method of adding percents when multiplication or division only. Method of adding, not a T, that's an F, of adding percents only for only for multiplication. Actually, maybe I'm just gonna put like a dot. No, I think I should spell it out. I was gonna put an X, but I'm like, well, I don't really denote multiplication as an X. And then we'll put a slash and then put division. Vision. There we go. No. N. And then you add the uncertainties, and then you can also find the other way around. Maybe since this is sort of an example, I think I will include it. We'll put an example area of floor. So we have something like that. I will put like length, and this is width. So we will multiply length times width. I don't know, I just said I don't use that way of multiplying it. But I'm gonna go see ya. Alright, thank you for stopping by. I appreciate it. Bye-bye. So we get this. And we have area, which is like a squared value, so... Well, I shouldn't put squared. Now, let's just do it anyways. Let's just calculate it by what I mean by do it anyways. So we get 12 meters squared. And then each one will put like 1%. Or no, it's the other way around, but I don't think that would change the final answer. So we'll have like this, then we'll put 1 plus 2% is equal to 3%. Then we can have this as an uncertainty. And if you want to report it as meters squared, you can take this to go backwards and get the actual unit of this. So we're basically just finding 3% of 12. .36 meters squared. So it can be reported as 12 plus minus 0.36 meters squared, or as 12 meters squared plus minus 3%. Yeah, so I guess these answers are both valid. Well, I just need to draw a box. Okay, there we go. These answers are both valid and they're the same thing. Ew. That's not good. If I draw it in sections like this, I can avoid. There we go. Are you kidding? I was like, I can avoid the stuff that I need to avoid. There we go. Precision of measuring tools and significant figures. Okay, my head is not blocking it yet. An important factor in the precision of my music stopped and I got an error on my YouTube. Hopefully it's fine. I got a volume error? Is my audio okay? Is everything okay? I tend to get these errors a lot, so it's probably fine, but just to make sure. Alright. Precision of measuring tools and significant figures. An important factor in the precision of measurements involves the precision of the measuring tool. So, it also depends on the tool. In general, a precise measuring tool is one that can measure values in very small increments. For example, a standard ruler can measure length to the nearest millimeter, whereas a caliper can measure length to the nearest 0.01 I was gonna say micrometer. That's not micrometer. Millimeter. This is not a micrometer. Millimeter. The caliper is a more precise measuring tool because it can measure extremely small differences in length. The more precise the measuring tool, the more precise the measurements. Very good. Okay, thank you. Thank you for confirming. When we express measured values, we can only list as many digits as we measured initially in our measuring tool. For example, if we use a standard ruler to measure the length of a stick, we may measure it to be 36.7 centimeters. We can't express this value as 36.71 because our measuring tool is not precise enough to measure 1/100th of a centimeter. It should be noted that the last digit in a measured value has been estimated in some way by the person performing the measurement. For example, the person measuring the length of a stick with a ruler notices the stick length seems to be somewhere between 3.6 36, not 3.6. Oh, 36.6 centimeters and 36.7 centimeters. And he or she must estimate the value of the last digit. Using the method of significant figures, the rule is that the last digit written down in a measurement is the first digit with some uncertainty. To determine the number of significant digits in a value, start with the first measured value at the left and count the number of digits through the last digit on the right. For example, the measured value of 36.7 has 3 digits, or 3 significant figures. Significant figures indicate the precision of the measuring tool used to measure a value. Okay, so important parts about this section. Let me change the color of my pen. We'll put measuring tools in sig figs. Tools, and ampersand and sig figs. So, where was that? There was like an important line. It was like the more precise measuring tool, the more precise the measurements. More precise tool, more precise measurements. Measurements. Yeah. And then we expressed measured values can only list as many digits as measured values can list as many digits as the tool. So values can only list as many digits as tools. Values list as many digits as tool. As tool. I think my voice is starting to go. For example, this significant values. So you can estimate the last digit. Can estimate last digit. Can estimate the last digit. And then for sig figs, the last digit written down is the first digit with uncertainty. So last digit written down and last digit is first digit. And first digit IRS, first digit with uncertainty. Put like a W as a width. I will make it look a bit better. With uncertainty. ITAINTY. Okay, and to determine the significant figures, start with the 3. Count the number of digits. So significant figures is equal to the number of digits. Sig fit. That's S. Sig figs was equal to the number of digits. Okay. Well, we got that part. Zeros. Special consideration is given to zeros when counting significant figures. The zeros in 0.05 are not significant because they are placeholders that locate the decimal point. There are 2 significant, number of digits non-zero. Non-zero. The zeros. Oh, but then, yeah, okay. Non-zero value. So if it's a pure zero, it's not like zero as in zero as a digit, but like zero as a value. If that makes sense. Maybe I'll put another thing like 0 as non-zero referring to value. Referring? Okay, let me just use that thing that I used. Non-zero referring to value. Not the digit. Not digit 0. Does that make sense? Am I explaining this correctly? But I like the example that they gave. So basically in this one, it's like 0.05, the zeros here are placeholders, but then if you have something that is like 10, technically there's a 0 there, but the value is 10, so that value is non-zero, if that makes sense. Are not significant. There are two significant figures here. The zeros in this are not placeholders, they are significant. So basically, if anything is before other numbers, then it's not significant, so you just count these. But then if there is a number before the 0, then you still count that 0. This number has 5 significant figures. The zeros in 1300 may or may not be significant, depending on the style of writing numbers. They could mean the number is known to the last digit, or they could be placeholders. Last digit as in like the level of uncertainty from up here, and placeholders as in just like this one, placeholder for the decimal place. So 1300 could have 2, 3, or 4 significant figures. To avoid this ambiguity, we should write this in scientific notation as this. Oh, I can't highlight. As 1.3 times 10 to the third, as 1.30 as 10 to the third, or 1.300 times 10 to the third, depending on whether it has 2, 3, or 4 significant figures. Zeros are significant except when they only serve as placeholders. So in this one, the 1.3 without the zeros only has 2 significant figures. This one, the 0 signifies the uncertainty of the measurement value. So there's 3, and that is not a placeholder. And for this one, there are 4s, because 1, 3, 0, 0, and that also signifies the uncertainty. Okay. Significant figures in calculations. When combining measurements with different degrees of precision, the number of significant figures in the final answer can be no greater than the number of significant figures in the least precise measurement value. So let's say multiple values, and then we'll put multiple values, and you say no greater, or sig figs no greater than the least precise measured value. Fig no greater than least. Oh gosh, I'm running out of space. I'll write down here. Precise measurement value. Yeah, okay. There are 2 different rules, one for multiplication and division, and the other for addition and subtraction. So the rules, a lot of rules. For multiplication and division, the result should have the same number of significant figures as quantity with the least number of significant figures entering the calculation. So the result should have the same number of significant figures as the quantity with the least number of significant figures. Okay, I see. So basically, if you have 2 values, one of them only has 2 significant figures, but the other one has like, I don't know, 5. You only report your answer with the 2 digits, or the 2 significant figures. For example, the area of a circle can be calculated from its radius using area equals to pi times r squared, or radius squared. Let's see how many significant figures the area has if the radius has, say, 2. So r equals 1.2 meters. Using a calculator with an 8-digit option, we will calculate this. But because the radius only has 2 sig figs, it limits the calculated quantity to 2 significant figures, or 4.5. So you can write multiplication slash division report sig fig. How do I say this? Sig fig value or number with least number of sig figs entering the calculation. With least number of sig figs in calculation. Least number of sig figs in calculation. That should be lowercase f. Well, I mean, that one's uppercase, doesn't matter. In calculation. Yeah. Usually during tests back in college, I would put up 2 decimal places because I'm lazy. Well, I mean, if you pass, then it works, right? That's all that really matters. Okay, so even though pi has like 8 digits, you use the one that has the least number of sig figs that enter the calculation. Okay, sig fig number with least number sig figs in the calculation. This is so confusing. How do I write this to make it sound better? I don't like that. Sig fig number with least number of sig figs in calculation. Maybe I put the of. If it doesn't fit, of. Erase this. I'll redo this part. Number of. Okay, I think that makes more sense. Least number of sig figs in calculation. Maybe I won't put with, I'll put like equals to, so sig fig number of your final answer should equal to the least number of sig figs in the calculation. Least number of sig figs. Okay, I guess that makes sense. Hopefully that makes sense. I think that makes sense to me. I'll move this up before my giant head blocks this. For addition and subtraction, the answer can contain no more decimal places than the least precise measurement. Okay, so no more decimal places than the least precise measurement. Suppose we buy 7.56 kilograms of potatoes in a grocery store as measured with a scale of a precision of 0.01 kilograms. Then we drop off 6.05 kilograms of potatoes at your laboratory. Why do you have food of potatoes in your laboratory? We drop off 6.05 kilograms of potato in your laboratory as measured by scale with a higher precision. I see. Then we go home and add 13.7 kilograms of potatoes as measurement by a bathroom scale with a precision of this. How many kilograms of potatoes do we have, and how many significant figures are appropriate in the answer? The mass is found by simple addition and subtraction. Okay, so you add all of these. I guess we have 3 bags of potatoes. Apparently one of them is in the lab and another one's in the bathroom. So we'll take 7.56 plus 13.7 plus this. Oh, no, we drop off. Okay. Okay, hold on. I'm confused on this question. So it's saying that we have this amount of 13.7 kilograms of potatoes plus this, but then you also subtract this. Okay, I see. Oh yeah, wait, it's right here. It's right in front of me. Okay, yes. But then you have to make sure that the decimal places do not exceed the least precise measurement, which would be the bathroom scale. So it would only have 1 decimal place. Yes, that makes sense. Next, we identify the least piece of precise measurement. So, yep, the 13.7 kilograms. This measurement is expressed to the 0.1 decimal place, or a final answer must be expressed to the 0.1 decimal place. Thus, the answer is rounded to the tenths, giving us 15.2 kilograms. I don't know why this potato example was so confusing, but I understand what is going on, at least. So add / subtract. Oh man. Okay, add and subtract. So then sig fig number is not actually based on sig figs in a way. It's based on the decimal place. Sig fig number is based on decimal place. So far I can keep up. Okay, that's good to know. Thank you. Based on least precise measure, based on decimal place of least precise measurement. Of least precise measurement, and we measure it. There we go. I think that works. That's a good explanation, right? So basically, if you have whatever is the least precise tool and the decimal place of that tool, or the decimal place of, I guess the smallest amount of, the smallest value that you get in your calculation, the decimal place of the, not the smallest value, the smallest amount of digits after the decimal place is what your significant figures should stop or start as. I need to get better at explaining things. Hopefully when I keep continuing this, I will get better at explaining stuff. Luckily, all of this I do actually partially remember. I did forget a bit about significant figures, but I remember the uncertainty stuff. So, but let's continue. Significant figures in this text. In this text, or yes, this textbook, most numbers are assumed to have 3 significant figures. Furthermore, consistent numbers of significant figures are used in all worked examples. An answer given to 3 digits is based on input good. I think good input is what there's input good. I think that's a typo. Based on good input at least 3 digits, or input good at 3 digits. Hold on, let me read this again. Furthermore, consistent numbers of significant figures are used in all worked examples. Okay. An answer, not example. I can't read. Oh my gosh. It's okay. I have one more section. I think this section is really short. And then the next time I'll do this, I'll go to chapter 2. But I can't read. An answer given to 3 digits is based on good input at 3 digits. Okay, for example, if the input has fewer significant figures, the answer will also have fewer significant figures. Care is also taken that the number of significant figures is reasonable for the situation posed. In some topics, particularly in optics, more accurate numbers are needed, and when we use more than 3 significant figures. Finally, if the number is exact, such as the 2 in the formula of the circumference of a circle, so 2 pi r, it does not affect the number of significant figures in the calculation. Likewise, conversion factors such as 100 centimeters to 1 meter are considered exact and do not affect the number of significant figures in the calculation. I see. So basically what this is saying is that in this textbook particularly, they usually just use 3 digits as long as it basically uses 3 significant figures. But if the answer has fewer significant figures, like if in the context of this book gives you a measurement with fewer significant figures, the answer of this book will also have fewer significant figures, and vice versa. So something that needs to be more precise. For example, optics, when they show you examples and stuff, it will have more significant figures as to which they want you to answer with more significant figures as well. There will also be times when you need to do unit conversion, and then the significant figures of that are, they don't care about it, it just doesn't count. And if it gives an exact number or an exact calculation, that number will not change the significant figures. So I guess this is just for like future reference of in the text. I think this is what it's saying. But yeah, okay. So let's try to review this section before I move on to the next one really quickly. And I usually highlight the most important parts. Well, I write the most important parts in blue, but in this case, I don't think there is actually that much. Like, I think all of this is important, so I'm just gonna underline the very, very important parts. So we'll put last digit is the first digit with uncertainty in a measurement. Significant figures is the number of digits. For many values in a calculation, significant figures are no greater than the least precise measured value. So this is very important. I noticed that everything has to do with the least precise measurement value, because that is also related to down here when you add and subtract. And this one is also to the least precise value in the calculation. Or I can write that though. Let me write significant figures are based on, in calculation, are based on the least precise value. Well, I guess this is decimal. Well, no, that's not true, because this is a decimal place. But I can still write in calculation. Look at decimal places in the least precise measurements. Look at decimal places, so that would be referring to the add and subtract. PLAC places and least precision in the least precise measurement. And then least precise measurement will be relating to the multiplication and division. Least precise. Precise measurement or value / measurement. Yeah, okay, that'll be the takeaway from this section. And then, are you ready for the last and final section of this chapter? And I do have a few announcements to make at the end, but they're not critical. Their announcements are nothing much, really, but I would be talking about like making this into a series and other future things. Final section. This is not the final chapter. I wish it was. The book that I'm using has like 3 editions and it's quite dense, but I think it's actually a really good resource for people who want to review like college level physics and stuff like that. Because it goes into a lot of things. I should put chapter 1, section 1.7. We're in chapter 1. Solving problems. Physics, why can't you solve your own problems? Why must I do it for you? I have too many problems of my own to solve. Whoa. Oh, this is just basics. Yes, we just started today. I just started this today. There'll be a lot more. I can't wait till we get to, I think it's chapter 3, where we actually get into velocity, position, and displacement. I think chapter 2 is about vectors, which is important. But yes, we are at the basics. Okay, solving problems in physics, learning objectives. By the end of this section, you will be able to describe the process for developing a problem-solving strategy. Yes. This is very important for anything. But most people have this skill down just from life. It's just hard to apply it to something like physics sometimes. Explain how to find the numerical solution in a problem. Summarize the process for assessing the significance of the numerical solution to a problem. Problem-solving skills are clearly essential to success in quantitative course in physics. I feel like problem-solving skills are the most important skill in anything. Most important, the ability to apply broad physical principles, usually represented by equations, to specific situations is a very powerful form of knowledge. It is much more powerful than memorizing a list of facts. Analytical skills and problem-solving abilities can be applied to new situations, whereas a list of facts cannot be made long enough to contain every possible circumstance. Such analytical skills are useful both for problem solving in this text and applying physics in real life. If you are probably well aware, a certain amount of creativity and insight is required to solve problems. No rigid procedure works every time. Creativity and insight grow with experience. With practice, the basics of problem solving become almost automatic. One way to get practice is to work out the text examples for yourself as you read. That's what we're doing. Nice. Another is to work as many end of section problems. Okay, I will not be doing this. However, if you would love to learn about this, I think this book has like problems and they show you the solutions as well. So you would like to genuinely really learn physics, end of section problems are nice. But if not, if you want to do it for fun, just like me, just to review, I will be doing the in-text examples, but I won't be doing the end of section problems. Starting with the easiest to build confidence, then progressing to the more difficult. After you become involved in physics, you will see it all around you. You can begin to apply it to situations you encounter outside of the classroom, just as done in many of the applications and in this text. Although there is no simple step-by-step method that works for every problem, the following three-stage processes facilitates problem solving and makes it more meaningful. The 3 stages are strategy, solution, and significance. This process is used in examples throughout the book. Here we look at each stage of the process in turn. So from this, what I'm hearing is that you have to come up with a strategy to deal with the problem. Okay. Why is my pen being kind of funny? Pen, please work. There we go. Okay, that seems fine. Strategy. Then you execute that strategy, find a solution. And then you find the significance of that solution. That's the basic problem-solving mindset or procedure. Strategy. Strategy is the beginning stage of solving a problem. The idea is to figure out exactly what the problem is, then develop a strategy for solving it. Some general advice for this stage as follows. Examine the situation to determine which physical properties are involved. It often helps to draw a simple sketch at the outset. You often need to decide which direction is positive, and note that on your sketch, when you have identified the physical principles, it is much easier to find and apply the equations representing those principles. Although finding the correct equation is essential, keep in mind that equations represent physical properties, laws of nature, and relationships among physical quantities. Without a conceptual understanding of a problem, a numerical solution is meaningless. Basically, you gotta understand the problem and what's going on. Then you have to make a list. What is given or what can be inferred from the problem stated. Identify the no's. Many problems are stated very sequentially and require some inspection to determine what is known. Drawing a sketch can be very useful at this point as well. Formally identifying no's of particular importance in applying physics to real-world situations. For example, the word stopped means the word stopped means the velocity is 0 at that instant, as we can often take initial time and position as 0 by the appropriate choice of coordinate system. So I guess this would be make a list of what you can find from the issue, of what you know and what you don't know. So examine the situation, find what you know, what you don't know, and what you can infer or assume. Identify exactly what needs to be determined, and the problem. Yeah, identify the knowns and the unknowns. So I guess I went ahead. In complex problems, especially, it is not obvious what needs to be found or in what sequence. Making a list can help identify the unknowns. Determine which physical principles can help you solve the problem. Since physical principles tends to express in the form of mathematical equations, a list of knowns and unknowns can help there. Yes, it is easiest if you can find equations that contain only one unknown, that is, all the other variables are known, so you can solve for the unknown easily. If the equation contains more than one unknown, then additional equations are needed to solve the problem. In some problems, several unknowns must be determined to get at the one needed most. In such problems, it is especially important to keep physical principles in mind to avoid going astray in a sea of equations. You have you may have to use 2 or more different equations to get the answer. So let's quickly write the strategy part. I'm not gonna lie, me personally, I think this section is a bit useless originally. But the listing of knowns and unknowns is super important, as that has helped me a lot, so I do like that advice. Read the problem, or look at the problem. Look at problem, find knowns and unknowns. My background music stop. Find knowns. Ampersand. Nope. Find knowns and unknowns. Yeah. And then equations. Find equations related. Not a G, a Q. Equations. Oh, equations. What? I clicked out on accident. Oops. Related. Yay! And that's a strategy. Let me put the music back up. There we go. Solution. The solution stage is when you do the math. Substitute the knowns and the appropriate equation and obtain numerical solutions, complete with units. That is, do algebra, calculus, geometry, or arithmetic necessary to find the unknowns. Being sure to carry the units through the calculations, this step is clearly important because it produces the numerical answer, along with its units. Notice, however, that this stage is only 1/3 of the overall problem-solving process. This is the hardest stage, but you can't really explain much about it, so next one, solution! Math time! Math time. Alright, significance. After having done the math in the solution stage of problem solving, it is tempting to think that you are done, but always remember that physics is not math. Rather, in doing physics, we use mathematics as a tool to help us understand nature. So, after you obtain a numerical answer, you should always assess its significance. Basically, checking things. Listing the givens and unknowns really helps a lot. By doing that, you are already halfway to solving a problem. Yeah! Honestly, I'm not gonna lie, I wish someone told me that before. But in the end, it really helps. Finding the related equations is also really hard too, depending on how many unknowns and knowns you have, but for now, we shall develop those skills. Math time! Check your units. Yes. If the units of the answer are incorrect, then an error has been made. Is my ginormous head blocking the screen? It is. Or it will. Has made, and you should go back over your previous steps to find it. One way to find a mistake is to check all equations you have derived for dimensional consistency. However, be warned that correct units do not guarantee the numerical part is correct. Check the answer to see whether it is reasonable. Does this make sense? This step is extremely important. The goal of physics is to describe nature accurately. To determine whether the answer is reasonable, check both its magnitude and its sign, in addition to its units. The magnitude should be consistent with a rough estimate of what it should be. So this sort of relates back to what I just was talking about at the beginning of the stream, is to make sure that it sounds sort of reasonable and that it's within a range that you think, okay, this could actually exist here, sure. Because if it's too big or too small, then it's probably not right, and you have to go back and check. It also compares reasonably with magnitudes order the same quantity of the same type, the sign usually tells you about direction and should be consistent with your prior expectations. Your judgment will improve as you solve more physics problems. Yes, this is true. I think because I haven't done that much physics in a while, my judgment for it has been quite terrible. But hopefully during this, it will get better in future streams as well, and it will become possible for you to take finer judgments regarding nature described adequately by answer to a problem. This step brings the problem back to its conceptual meaning. If you can judge whether the answer is reasonable, you have a deeper understanding of physics than being able to solve a problem mathematically. Check to see whether the answer tells you something interesting. What does it mean? This is the flip side of the question. Does it make sense? Ultimately, physics is about understanding nature, and we solve physics problems to learn a little something more about how nature operates. Therefore, assuming the answer does make sense, you should always take a moment to see if it tells you something about the world that you find interesting. Even if the answer to this particular problem is not very interesting to you, what about the method to solve it? Could the method be adapted to answer a question that you find interesting? In many ways, in answering questions such as these, that is the science progress. In these that science progresses. Oh wait. In many ways, it is in answering questions such as these that science progresses. Science progresses. Wow, I can't read. Anyways, that's the end of this chapter, so let me finish writing the significance part. I think my music stopped again. It doesn't like me. Basically, if I'm on for too long, I use like a YouTube playlist so that all my music is copyright free. Oh no, it's still playing. I just can't hear it. Never mind. But sometimes it'll stop because it's like, why have you been playing the same playlist over and over again? Significance! Units! This is extremely important. Check your units. Checking my units has saved me a lot of questions. Reasonable? And interesting. But yeah, that's this section. Here are the notes that we took today. That's actually a lot more than I expected. But yeah. So we went over estimating values, just like whether or not to find whether some value is reasonable, to estimating values, estimating the mass of the Earth, the oceans of the Earth, and using the principles of like geometric mean and trying to find when something's bound or not. And then we also talked about significant figures and how to report your answers with uncertainty and discrepancy, and how discrepancy and precision are related. Discrepancy and accuracy are related, and precision and uncertainty are related. How to navigate significant figures with multiplication, division, and subtraction, as well as tools that have varying precision. And then the process of solving problems, and quite frankly, the scientific process in a lot of ways. But yeah, I hope you enjoy this stream. I do think my voice is gonna go out. I think next chapter... Vectors! We are gonna learn about vectors and what magnitude and scalar means. Or magnitude and direction. That reminds me of that like villain from Despicable Me. But displacement and magnitude. And yeah. But yeah, I hope you enjoyed it. As for announcements, what I wanted to make was, before you go, if you haven't already, please comment on, I am trying to look for a community name, so if you would like to comment or would like to share your opinion on something, let me get the link to it. I've only seen 4 people comment on it. But, oh man, I wish I had my I wish I had my software that combines streams, because right now it's a little half broken. So please comment on that post if you would like to be involved with naming the community. That would be much appreciated. It is on YouTube only, so sorry if you're on Twitch and you don't want to use YouTube. Use either one, it's just because YouTube has a community post section, so it makes everything easier. And another announcement is that I will be taking a hiatus near the end of March and the beginning of April. It will probably be like a month and a half. Unfortunately, life has been a mess. It's not a bad mess, but it's been a little bit much. So I will be taking a hiatus during then, and hopefully after my hiatus, I can announce something really big, and I'm really excited for that to happen. I've been cooking since December, and I will finally announce it mid-April, I think. But yeah, usually during hiatuses, I post videos in between to not give to, like, I post videos or whether it be like a stupid cover or something, but I think this time, unfortunately, I can't do that. But when I come back, I'll have really cool stuff for you to see. But yeah, basically, I have a few more weeks to stream, and then I'll be going on a month and a half hiatus. I'll finalize the dates and post it when I'm ready. But yeah, that's the second big announcement. But I'm so excited for April. When I can finally reveal things, I'm gonna be so happy. Like, I don't know. I feel like I've been hinting this for such a long time, but it's taken a long time for me to set this up. I will try to find someone to raid on Twitch. So if you're interested and you would like to go, feel free. But if you can't, no worries at all. Please take care of yourself. Let's find someone. That's the raid message, if it will load. Hopefully the bot is working. Let's see who's on. Maybe I can't find anyone who's on. Someone is playing the headliners. They are very cool. They're playing with other people as well, so I think I'm gonna raid Zell. Okay, this is more scuffed. This is more scuffed. I'm sorry. Hold on. Okay, there we go. But yeah, if you would like to join the raid, that'd be much appreciated. If not, it's totally fine. Thank you for learning with me. And oh, right, another thing. I hope to do these physics streams once a month, besides the month that I'm gonna be taking a hiatus. But yeah, hopefully see you next month. If you like to learn physics, I do other things as well. Not tomorrow. Next week, I'm probably gonna play web fishing and Baldur's Gate. But yeah, I still have to do part 2 of my celebration. But I will stop yapping and go to here, mute that. We'll raid in a few seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Beep boop. Bye everyone. Bye bye.